Good evening. Thank you for your patience. Thank you for joining us this evening in person and online. We are very excited to welcome one of our inaugural Design Tech Innovation Fellows who is giving a lecture this evening, Marirena Kladeftira. This is the last lecture in the Design Tech lecture series for the spring. And I just wanted to mention, if you haven't had a chance to see our inaugural Open Studio exhibition, which is just next door, it will be up through Friday, which is an amazing cross-section of work of our faculty, our fellows that are with us for the year, and of course, our amazing students. So with that, I'm going to invite Lawson Spencer, who is currently an instructor in Design Tech, to introduce our speaker this evening.
Wow, this is exciting. Marirena Kladeftira is a Design Tech Innovation Fellow at Cornell University in the Department of Design Technology. Marirena's work broadly investigates the challenges of design and digital manufacturing as it relates to notions of automation, human agency, sustainable reuse practices, and critically questions a technologist's role in the era of the Anthropocene. Before coming to Cornell, Marirena completed her doctoral studies at ETH Zurich as a doctoral fellow at the NCCR, National Center of Competence and Research in Digital Fabrication, which is an architecture and construction research institute funded by the Swiss National Science Foundation. Marirena's dissertation, Capsules of Complexity, additively manufactured connections for a non-standard space frame, strategically questions how tools and techniques of digital fabrication with respect to various material constraints could inform new geometric solutions for scalable, safer, accessible, sustainable structures that ultimately produce less waste compared to typical solutions. Following her defense, Marirena became a postdoctoral researcher at the EPFL, where she worked between the Lab for Creative Computation and the Structural Exploration Lab. Marirena's work has been exhibited at a number of places, including the Venice Biennale, the Swiss Sustainability Forum, Swiss Robotics Day, and most recently, the Design Tech Open Studio exhibit in the Bibliowitz Family Gallery. That's across this wall. She has published several journals and conferences, or she has been published in several journals and conferences such as Fabricate, Acadia, AAG, ICSA, IASS, 3D printing and additive manufacturing, and many others. She has received several grants, both as a lead PI and co-contributing PI. She is also a licensed architect engineer. And since coming to Cornell, I've been very fortunate to work very closely with Marirena on robotics and have learned an enormous amount from her. One day she told me she enjoyed robotics kind of as a means to an end because of the math behind it. And as she started explaining a small portion of it to me, it was going over my head. I was a little bit overwhelmed. I started to zone out and I was like, was I just fed the capsule of complexity? So Marirena, both you and your work are incredible and a huge inspiration. Thank you so much for sharing your work with us today.
Thank you, Lawson, for this too generous introduction. I'm super happy to be here. I'm, as Lawson said, one of the 4 innovation fellows that joined the department here at Cornell this year. I did complete my studies at ETH Zurich, and I was for a year last year a postdoc at EPFL before joining Cornell this January. So it's been a short time here, but alas, very inspiring so far. So today, with my work, as you will see, I explore how digital fabrication technologies can contribute to eco-social sustainability in architecture, specifically looking at lightweight and circular systems that respect place, craftsmanship, and local resources. And I often advocate for hybridity, which is a key theme that you will see throughout what I will present today. And as architects, I believe we are often fascinated with singularity, monolithic structures, single processes, omnipotent machines, perhaps because the act of making is so complex and buildings are so complex. We often imagine this one machine that could build our buildings in one material in a single process. But there is also intelligence embedded in plurality, where perhaps every material, every agent and process and part is purposefully employed within a system. And I titled this talk Post-Digital Perspective because the term post-digital really positions this work in an era where we imagine technology to be perhaps now pervasive. Our envisioned global automated models of making perhaps are challenged. And in my perspective, we must question what is our charge and our responsibility as architects. How can we design technologies and technological systems that are situated in their respective contexts and in a human-centered approach that respect the nuances of place, ecology, and human well-being? And so with my work, I really ask, how can we rethink our constructive systems with technology in order to ethically respond to an ecosocial crisis? And to do that, work in close collaboration with different disciplines in engineering, science, and also the social sciences. I work with craftspeople as technology really becomes the medium and the platform to mediate between these different fields of knowledge. But before I move forward, I also want to talk about something a little bit that is not so common, which is my research lineage that I think might help better position my work today. And by research lineage, I don't necessarily mean inherited ideas of a place, but rather how ideals and values have transcended generations. So we can say that kind of my great doctor, intellectual father was Konrad Waxman, who was author of the universal space frame and the package house system, and who pursued in tandem with Fuller and others, a light and kit of part systems for a global economy. And his ideas were kind of inherited by Fritz Haller, who was author of the WSM system, who are in offices of architects all over the world. And he was influenced by these ideas of adaptability, systems, and cybernetics. His direct mentee was Ludger Hovestad, who came to ETH Zurich and expanded these ideas into kind of the digital realm, later influencing my direct mentor, Benjamin Dillenberger, whose work explored systems for data-driven form generation. So as my ongoing PhD was moving forward, and we're very often discussing this kind of like lineage of ideas, and it was kind of bestowed upon me to carry it forward, I think you will see how this work incorporates bits and pieces of these notions, extending perhaps beyond the digital, how modularity, localized mass production, and the future of making intersects with local and global models of production, and also the democratization of production means. So I believe that no act of making is neutral, and architecture, specifically before the Industrial Revolution, was deeply rooted in place, in community and local craft, and always kind of sat at the intersection of many parameters, disciplines, contexts, affecting its environment and social values at smaller and larger scales. And we know that actually construction is a huge contributor right now to climate change. Our systems are not working. We also, it's the industry that most depletes our natural resources. And somehow we still actually need to double more or less our material consumption by 2060 just to meet the expected construction demand. And this is only these materials that should end up as landfill at the end of life of our buildings, because this is the model we were used to so far. At the same time, we have seen in this turn and this climate urgency that for the first time, courts find even countries at fault for not taking action for climate change, invoking rights law. And we need to understand that we have a huge share of that responsibility. At the same time, we really live in a world that is engorged with the digital, where technology has permeated nearly every aspect of our existence, where we start to question the boundaries between humans and machines, and we create new types of robots to coexist with us. And yet somehow construction is still very behind compared to other sectors. We're apparently the industry with highest resistance to change, even though we don't only contribute to emissions significantly, but also there are problems. For example, we have a lot of skilled labor shortage. It's making the headlines every other month, to the point that we now look at minors joining the workforce. Tackling these weekend problems is, of course, very challenging because of the complex interdependencies and changing requirements. And in my perspective, we need to take a different approach, challenging existing systems and developing new ones for the digital age, incorporating digital technologies, rethinking design and making as a process and not as an end product, and radically transforming the future of work in design and making. A concept that was introduced by social philosopher Friedhof Bergmann, who actually argued that technology will serve people by allowing them to be more creative and collaborative, increasing their well-being and vocational fulfillment. So instead of talking only about function and form as we're used to, we should also be talking about interactions, actors of making, materials, and energy flows embedded within our systems. And I think it's not trivial that over the course of history, any attempts that have been made to automate parts of the construction process have kind of failed. None of them has seen adoption. This might have been because of this idea of single task automation. But in my perspective, I believe that the future should be local and multi-process to be resilient, a kind of synergy of digital and standard processes, machines, and humans. And many speculate actually that our domain actually might entirely skip Industry 4.0 to jump directly to Industry 5.0, which is a vision where the driving values are actually sustainability, resiliency, and human-centric development instead of full automation. So my work really looks at technology as the key component for doing that, for authoring adaptive and local fabrication systems to achieve carbon neutrality, while constantly employing technology with a forward-looking take on the future of work in the different sociocultural settings. And current researchers out there to author more sustainable systems, they look at this kind of lightweight or modular structural systems, the use of regenerative and local materials that we can find locally, as well as circular building practices, this kind of like kit of parts that can be used over multiple life cycles. Interestingly enough, space frames encompass all of these qualities. They are lightweight, they are modular, they're very efficient structural systems and can take many forms. But the current systems that exist in industry are mainly monomaterial, have very limited configurations, and that is to reduce the logistics and complexity for their joint fabrication. And so this was the idea that kind of sparked the beginning of my doctoral work that was titled Capsules of Complexity, which reflects this idea that joints in architecture not only hold the transitional space, but they are the mediators between materials, forms, and assemblies. They articulate space, but also define aesthetics. And they're also the key components that determine the assembly of the structure, how disassemblable and circular it is, or reconfigurable. And for me, that really creates an opportunity to encapsulate all these parameters very efficiently in these very small components. So by distilling intelligence only in these very small parts, we can have maximum impact on the performance and formal quality of the structure. And we can also start to think about hybrid and multi-material systems. And with 3D printing, we have now also new opportunities to fabricate these adaptive structures. But unfortunately, much of the research up to that point looked at these components not as design objects, but kind of like parts that we can optimize to reduce our material only in these small components. However, when we employ hundreds or thousands of these elements within one structure, I argue that there are too many factors to consider that open up also new opportunities. And we need to tackle this in a more holistic manner. And we can use and concentrate all these parameters around perhaps 4 pillars that have to do with the design at all scales, the materials that we employ, and the manufacturing methods that we use to fabricate them, and the assembly of the whole system. And based on those, to understand it better, but also its ecosocial footprint. And so in my PhD, I created a design and fabrication framework centered around and mediating between these parameters. And this was rooted also in a vision for a decentralized prefabrication where we can design anywhere in the world with local intelligence. We can seamlessly send our fabrication data to a local network of digital manufacturers, distributing the bespoke fabrication of the smallest parts of the building systems. Those can be efficiently shipped on site just in a few boxes, and they're with locally available materials. And with the help of digital technologies, we can build resourceful and performative structures. And I had the opportunity to test this on different structures during my PhD that examined and furthered different aspects of this framework to achieve ultra lightweight systems that use as little resources as possible. So focusing a little bit more on the design methodologies for bespoke connections, as I mentioned before, the existing research looks at a couple of pathways. One is the use of topology optimization in an effort to reduce material. The other is kind of using implicit modeling, which I will explain in a second. But I actually propose that there's a better way to do that. We can use implicit modeling for the description of those elements. And there are a few advantages to that. So by explicit modeling, what I mean is a description of geometry with what we know, points, edges, surfaces, but actually implicit modeling is kind of a lossless representation of geometry, if you will. But as it defines geometry as the locus of a distance function in continuous space. And so that creates an opportunity to modularize the joint design in discrete functional components, which I did with devising a design tool, drawing also from a vocabulary of details with specific geometric and functional properties. And those can be combined and fused together at will with very simple operations on mathematical functions. So complexity in design comes at no cost. And by assigning parameters and functions that relate to specific desired geometric features at all scales in the computation model, we can basically program each granule of matter within the structure and tailor each connection for its specific location, add special requirements for the assembly or local transformations, and tailor material-specific constraints when working with hybrid material systems while still maintaining a coherent architectural vocabulary. So for example, with this framework, we can explore how we can rethink ultra lightweight structures using regenerative low carbon materials like bamboo. And so I developed this project that was called the digital bamboo, which is essentially a lightweight structure made of unprocessed bamboo canes and 3D print connection that negotiates also this equilibrium between biogenic and artificial materials, standard and bespoke parts. And this system is extremely lightweight and efficient. It weighs only 5 kilos per square meter. It spans 10 meters and covers an area of 40 square meters. What we also know is that although we know that the global material use will continue to intensify, actually most of the construction activity that is needed globally is in the south. And what is interesting there is that bamboo is a local native material to the south. It is scalable and renewable. It grows very fast, and also its tubular shape performs very well under axial loading. But because of the natural variability it has, it's not really compatible with our standard systems. And when these composites have been attempted, we see this kind of situations where mortar or cement is cast in the poles to establish non-reversible connections with material that actually massively exceed bamboo's mechanical properties. But I argued that we can identify better material pair with a manufacturing decision framework that I developed. In this case, that is polyamide. It has comparable strength to density ratio to bamboo and lower embodied carbon than metals, for example. And if we look also at the available manufacturing techniques for that, multi-jet fusion offers actually a very high degree of resolution that we can use. And so I was teaching a studio at that time. We started to experiment a little bit on new joint systems and kind of informally tested them because it was COVID times actually. But in the process, I observed something that was really interesting, that this kind of knot connection actually performed better than any hinged connections using a pin, for example. And that was kind of an interesting idea as a compromise between performance and easy assembly without post-processing the bamboo that we had at hand, which was really key for me. And at this point, I started collaborating with a group of structural engineers. We performed a series of destructive tests to actually understand how the system works and also continuously evolve and improve that connection, taking into account also the mechanical properties of that specific 3D printed material, which was kind of new at the time. And we also derived a model with graphic statics to kind of understand how stresses are within the material and how forces transfer from one component to the other. And the final joint connection you can see here, it features two standard externally interlocking components and displays this rotational freedom that helps a lot with the assembly and acute angles. And we always have these two parts. The core, which is always the bespoke part, is actually minimized as much as possible, whereas the caps are kind of standard and can be mass produced even and reused in different projects. And this system is really specifically easy for human assembly, as it is intuitive and can be used in various contexts by lay people. So this quick evolution of joint designs that I showed was really only possible because of this very streamlined design framework where all the relevant components are fused together for each joint in its specific location. And here I have a small video that shows some of the process that were involved. So the students were part of the initial design process of the pavilion. And we had some limited capacity to fabricate because it was during COVID. But then the panels that you see on top were actually also a method that we started investigating at the time, where we 3D print selectively material in between a lightweight textile that forms these catenary shapes to keep this kind of ultra lightweight theme throughout the structure. So after we had the initial exhibition in the museum in Zurich, we were invited by the European Cultural Center to exhibit this structure during the Venice Biennale of 2021. And so we actually disassembled the pavilion. We flat packed everything in, I think, 2 or 3 boxes and put it in a truck and reassembled it on site with the people that were there that had no knowledge actually of the system in just 3 days. And in this platform, we could showcase how combining these unprocessed biogenic materials with these digital components can lead to these hybrid systems that have lower footprint, very minimal on-site time construction, and can be really designed for disassembly. if you notice that the center of the pavilion in the video before, we had this extreme case where one joint actually received 24 members. That's roughly 300% more elements than your average joint. There was high shear stresses in this connection. And so due to this complexity, I designed a different type of connection there that was 3D printed in steel this time using conventional metal laser sintering technology. And although direct 3D printing of steel was used for this one very small part, it was really disproportionately expensive, time and energy consuming than the rest of the processes in the pavilion. And in my search for this kind of low cost, high resolution production methods for metallic components, I kind of reviewed everything that is out there, and I discovered that there is actually a gap. And so I initiated a collaboration with the German Fraunhofer Institute to look into complex low-impact metal manufacturing. And some researchers there were looking at a process called gel casting, which has been used for the production of complex ceramics in the past. And the idea was to transfer this process for steel components that can be produced with really low cost at large qualities. So what does this process look like? We have essentially an aqueous solution that has a high concentration of metal powder suspended in a gel. This is cast at low temperatures into 3D printed polymer molds that you can produce even at home. This cast is then left to dry at room temperature, and then it's introduced into a solvent bath where the mold is dissolved, and so it exposes the green part. And this is then introduced into an inert oven where the part is decreased, the polymer, extra polymer is burnt, and then it's sintered to reveal the final part. So this process does not only require lower energy, it is low cost and has almost 100% material utilization. If you ever worked with material sciences before, you would know that actually us achieving what you see on the left, which is about a 2 centimeter small complex piece, was already a huge success for them. But actually it's not still very relevant for architecture. So we had to find out how we can scale up this process and how to do that. And so I brought home some material and I started testing what might seem here a bit randomized tests, but actually there were fundamental tests to discover some properties and limitations of the material that you would get with your normal material spec. I was also very lucky enough to have a lot of experience from past projects in mold making for metal castings. I had worked very closely with foundry workers to understand their mold making techniques for mold complex shapes, and had monitored how metal flows within molds, the cool down rate of the material, where cold joints form and stresses develop. And so leveraging that knowledge and working with the master's students during my doctoral studies, we basically developed a new computational molding tool that is specifically designed for gel casting, respecting the nuances of that production method. And so after about half a year, we were able to produce successfully a connection for the same function as the one that was placed in the digital bamboo, but with only a fraction of the cost. And what was also very interesting is that what was initially used, it actually weighed at almost 4 kilos, and that was really because of the limitations of the technology, where you have to build a lot of support structures during fabrication that cannot be removed later on. But with this new technique, we can actually have a lot more freedom in the form generation, and we can fabricate much more complex shapes without any support structures, but sinter them in a sunbed. And the cost was also basically reduced to about a fourth. Earlier, I also talked about how assembly also affects structure, modularity, and joint design. And the digital bamboo was specifically designed for crowdsourcing the assembly of structures. But if we also take a look at how the industrial space frames, especially bespoke ones, are erected today, safety of workers is at stake while they hang at these incredible heights, and often the scaffolding works required are so dense, we must essentially build a building twice. So I was asking, can we use perhaps bind-inspired principles or swarm robots to assemble space frames, and what are the details that would allow that? There has been research in this domain in robotics, for example, where drones form these structures mid-air for navigation, or others where the builder robot is part of the structure itself, or it's moving in synergy with the structure. In some instances, even when detached, the modules still have this embedded electronics to communicate with their builders. And actually, my idea was to remove a little bit all of that complexity and perhaps look into using general purpose drones or cargo drones. Can they just carry the modular elements and put them in place, and instead embed all that intelligence of localization assembly into the joints that can be fully customized? So we're moving then from a hardware software problem mainly to a navigation and design problem. And to kind of start to understand these practices, I started collaborating with the Robotic Systems Lab at ETH Zurich to explore how these 3D printed connections can achieve self-assembly of structures if modules are just dropped by drones, exploring the self-guiding details and chains of magnetic polarities that would allow these modules to be dropped and self-assemble on air. We did some investigations into 3D printable localization markers, variable densities to reduce weight. And in the interest of time today, we'll actually skip this project, but these fundamental investigations of these multi-interlocking parts kind of formed really the discourse for the next project I want to show, which is Protoplasto, that looked at really pushing the limits of lightweight construction to what we can say almost ethereal architecture to achieve this kind of assembly for the limited payload of aerial robots. This is a structure entirely made out of plastic, a material that most recently, in light of sustainability concerns, has been vilified in our discipline. But once plastics were actually the epitome of future building projects, like the Monsanto house provided a discourse in the 60s and 70s around lightweightness and how plastics would revolutionize all products from utility items to buildings. And for me, the discourse today is actually how can we be resourceful about their use, their life cycle, and turn to biodegradable alternatives. So protoplasto, it means the first formed in Greek. It's an ultra lightweight media installation that is composed of a modular radial space frame that you see on top that can be assembled scaffold free and is supported by lightweight 3D printed columns. The modular space frame of the canopy is formed with the set of cantilevering meridians and a set of parallels that define the assembly layers and also the modules. And then there's an internal subdivision that is applied that stiffens these different modules. And what you can see here is actually the variable modularity of connections that is needed to achieve this kind of assembly. So we can assign basically any of three typologies of joints to each of those points. We have the intramodule joints that have specific details for cord and web members, the primary modular joints that are designed for this semi-constrained assembly, and also the lateral modular connections that are part of the outer ring of the structure. And so by assigning this variety of typologies into this color-coded diagram that you see here scattered across the structure, we can achieve a radial modular assembly scheme, as you see here, thanks to the self-interlocking system. And what is interesting is that now each of these modules weighs around 3 to 5 kilos, which is easily within the range of payloads of drones. And this can be lifted and assembled even by a single person without any heavy equipment or any support structures needed. And this roof was so light that we had actually the opportunity to rethink entirely the material systems of the columns. by inventing a new method called hollow core 3D printing. So what is hollow core 3D printing? Conventional 3D printers extrude a massive circular bead that really also limits the buildup rate of these components. And what we developed is a new system where we actually split the material in the nozzle and introduce positive air pressure, thus inflating the bead as it is extruded, resulting in a 10-fold increase in layer height and significant reduction in material. We also take advantage of the strength of tubular shape to do this. And with this invention, we can really achieve very high buildup rates, printing 1 2-meter column in every more or less 4 hours. That is really comparable to concrete 3D printing, for example. We also developed a variety of custom nozzles to tailor the internal channels, increasing the strength or creating differentiated air pockets within these structures at the meso level. And so because of this thin cell of that material, we also have an added benefit, higher transparency than normal 3D printing, that we took advantage in this case to embed the lighting of the installation that we did. So this was initially also part of a studio where the students were invited to rethink how we can design these modular structures. How do we think about modularity and relationships between these prefabricated elements? And then they were also involved in the assembly of the pavilion and explored different types of assembly guidelines, in this case, AR, to kind of guide them to do that. So we initially actually called the system the one human roof because it's so loud it can really be assembled by one single person entirely. And to give again a little bit of perspective, your typical space frame weighs about 20 to 25 kilos per square meter, but this structure only weighs 3 kilos per square meter. And with this hybrid material system, we try to give this, again, new perspective on using the synthetic materials for architecture, minimizing resources to absolute necessity and designing for disassembly so that all materials can be then recycled or reused at the end of life of that installation. And so after doing some work in this area, I realized how the trade-off between relieving humans of this unsafe task actually introduced more and more complexity and in autonomous systems, sidelining a bit the benefits of agility and human craft that was present in my previous body of work and work that I did not show today. So I was really curious to explore the space looking into collective agency of humans and robots as a powerful partnership that can increase agility and reinforce local crafts while still decreasing the risks and hazards for workers. At the same time, in Switzerland, where I was, they started to put more and more pressure on sustainability mandates in new buildings. And after some discussions with actually one of the industry partners that was part of the previous project, who was a developer and contractor company, I realized that they were very interested in finding digital pathways for reuse in existing infrastructure. And I thought that's a great place for me to jump, as we're not dealing anymore with these super precise elements I was making, but actually this is a space with a lot of uncertainty and factors we cannot account for a priori. And I can tackle this topic head on, how we can co-work with robots for assembly and disassembly, and perhaps some of this work might then feed back to the previous hypothesis. And we know that actually more than 36% of generated solid waste in the EU and also in the USA is actually from construction and demolition activities. So again, a lot of potential to reduce carbon footprint if we extend the life of our buildings or turn to urban mines and think how can technology help us meet these new requirements with the uncertainty that comes with it. And if we do actually use machines and robots to do that, what about their accessibility to a retiring workforce and increasingly more non-skilled people? And there's a strong argument to be made here, as this type of work is primarily manual and it's really taxing to workers. And I talked earlier about how we are facing lack of skilled labor. We are also substituting with unskilled labor, but in fact, if we also take a closer look at the demographics and stats for conditions in the industry, we have a lot of mental challenges, unhappy people. Construction has actually almost a 50% suicide rate, which is second to mining. And perhaps technology can relieve some factors associated to these results. On the other hand, field work and construction is primarily a man's job. Women in the trade account only for about 10%, and only 2% of that is actually in the field and not in office jobs. So what if we could change entirely the profile of this type of work? Could we increase access along with better conditions? And looking into the Swiss context, there's a lot of timber structure that either experience damage due to catastrophic events or have simply been outdated. And so challenging our existing methods, I looked at how hybrid teams can work collaboratively to deconstruct, repair, and reconfigure damaged structures without actually any material leaving the site. And I was asking, are there intuitive ways of collaboration and intervention between humans and robotic agents? Can we transfer tasks from one to the other and relieve the human of these unsafe and difficult tasks? Lucky enough to be at the right place at the right time, I actually found some material of a deconstructed old chalet in Switzerland. There was about 30-something beams of structural pine wood. And as we wanted to reconstruct essentially in a lab setting, a traditional Central European timber frame. And around the same time, we'll take a small detour here, but I was working with master's students who was, in his thesis, he was really curious about how we can rethink craftsmanship with digital tools. And so we started discussing about this case study that when the roof of the Notre Dame had collapsed, after all these conversations and competitions and whatnot, they actually decided to rebuild the timber roof using the artisanal ways that they had done in the past. Our conversation was, can we actually use new tools to reshape our crafts while still being relevant to our heritage? And so Alberto, my master's student, he visited last spring the atelier that actually reconstructed that roof with the old craft of hewing, and stayed with the workers and artisans to learn how they work and which actually components of the work they enjoy. What is hewing? Hewing is really centuries-old process of squaring wood logs. The bark is removed. Then these lateral notches are made in all four sides that follow actually the curvature of the wood to retain as much material as possible. And the excess material is removed with an axe, retaining as much material again. And splitting, the axe also splits the woods along the natural fibers, and so it makes it less susceptible to infections and natural degradation compared, for example, saw cutting that opens up the pores instead. And the wood is also air dried, it's not kiln dried. So there are energy savings in that as well. So what you see here on the left is Alberto. He actually went there, learned the process, and then we started to rethink how to hybridize this craft. And what we found out through interviews is actually that the part the craftspeople enjoyed is somehow what you see here, the last part, which is kind of a meditative act for them. They perform it in nature. It has a special relevance and meaning to them.
Avec ces camicoles répétées, on a des milliers de mètres cubes de bois d'Autrichier qui sont de basse qualité qui arrivent sur le marché. Et qui sont tellement là qu'on est en train de mettre en bois énergie des bois qu'on attaque pour la construction. parce que le bois énergie paye plus, surtout une boîte de construction qui a chuté, c'est pas permis. Mais ça, c'est les architectes qui doivent prendre conscience qu'on peut les utiliser. Il y a la même charge mécanique.
And so we actually stumbled upon some wood that the city of Lausanne actually discards every year, either because of the health of the forest or material that is considered waste and is not needed anymore. And we could recuperate that. We brought it back into the lab to work with it because for us that had potential, new potential for construction. And so we had the robot scan the material, and based on the natural curvature, it kind of assigned these variable notices that before were performed manually. And also the robot could cut all the joints that would later be needed very precisely. We could finish that by hand when needed, and then
il y a une simplicité dans le procédé constructif qu'on fait à la main. On n'y arrive pas avec l'industrie. Prélever des arbres, même les moins jolis arbres, à 5 km, et puis les transformer en poutre à la main, on a moins de perte mécaniquement. C'est la façon dont on va pouvoir s'adapter à une on va pouvoir s'adapter à de l'oublier, à du flash.
and then the last saving was still performed by hand as it was whisked by the craftspeople. So why I saw that coming back to this reconfiguration project, we were able to take all of that knowledge of augmented carpentry to build our structure the artisanal way. So we did it like the old masters did it. We laid the beams on the floor. We had the robots to create all the joinery that sometimes needed to be finished by hand. And then we fabricated a traditional wooden frame as one would find it in various regions of Switzerland. And interestingly, a lot of the challenges that we were faced in this deconstructed the structure had to do with the specific jointing techniques that were used in the specific place. So for example, some of the connections are coplanar and face the same direction, which can be removed very easily. Others, though, might have conflicting directions of disassembly, can be locked by third elements, or feature more complex interlocking connections that cannot be removed. And some might even be positioned in places outside of the robot's reachability map. And so the workflow looked something like this. It blends existing practices with autonomous ones. The human performs a reclaim survey at the beginning to identify grades and visual cues and take measurements like humidity levels, and etc. And then the two robots were equipped with stereoscopic cameras, grippers, and a chainsaw. They scan the structure, creating essentially a kind of digital twin from which we can abstract also a structural model for further analysis. And we can also encode the joint connectivity within that. And then the workers can take actually decisions based on both qualitative and quantitative data, after which they can collaborate with the robots in reconfiguring the structure, constantly updating its state in the digital model. And the goal was to essentially take this damaged European style framing into something that actually not only serves the new requirements for space, but actually it resembles more like a Japanese style framing where rigidity is achieved through the superimposition of parallel members, and those can be easily disassembled, ensuring further life cycles of materials. And again, this video, I think, shows some of this ongoing process, rethinking how might we cooperate in this kind of situated context and share tasks that need in situ decision-making and expertise. And this hybrid relationship give maximum agency to the human to basically make on-the-fly decisions that need to be for different things that need to be accounted for. So which materials should be repaired or downgraded with information from the digital model, we can basically decide on the sequence of actions that need to happen. And so robots might support, cut, remove, add components based on the human's instructions. They can also collaborate, passing material from one to the other, and vice versa. The worker can actually support the robot in its tasks by, for example, releasing connections that require more agility, perform cuts, or other tasks where the robots have limited reachability, for example, close to the ground. And the goal here was really to make use of each actor's best strengths, release the workers from the heavy tasks of carrying loads or operating in safety hazardous zones. And as you saw, this doesn't happen behind some closed fence. It's really a strategic partnership where we can be a bit more strategic about each actor's role in the structure. We were also very happy to be invited again to exhibit this work, which is finishing within the next 2 weeks, I would say. And then we will exhibit it in Venice from May onwards until November. So if you happen to find yourself there, you're more than welcome to check it out. So working in these kind of changing and hazardous environments also made me question how we can make the communication between these different actors more intuitive, increasing access and trust to people that don't have the skill set to operate robots, or even extend perhaps the workforce, as I said, to women or other minorities that can leverage the precision and payload capacity of them to enter the workforce. And I was supervising a doctoral student at EPFL who was looking into methods of interaction with construction robots. And this kind of like mutual interest brought us together to develop a new process and protocol to communicate and instruct remotely construction robots using essentially a system of props that you see here. So much like an architectural model, which was a very interesting medium for us because architectural models are an essential and intuitive tool of understanding structures and space in our discipline. They have historically been the primary method of practice for architects, engaging both corporeal and sensory cues with our cognitive process of design. And so we actually designed this kind of like low-tech system. You can even call it a sort of toy with which you can experiment as you would do with a model to build a structure. And with that same toy, actually instruct a robot to build it in real scale. And the workflow looks something like this. It's really an interactive cycle as one would engage with a model. So you can create something, the robot, and scans the structure. And we use computer vision to create essentially a digital twin of the model, which is then using a computational process, rationalized and transformed into fabricatable tasks in real scale. And then we have the motion planning and the robots build it essentially collaboratively in real scale. Of course, you can go back, make changes, add new ones, and continue the process essentially. This was our very simple and entire kit of parts to do this. And what was actually a happy realization is we had the opportunity to take this process to two workshops last year in the Design Modeling Symposium and the Future of Construction, and have participants actually engage with the system. And it was a great educational tool, we found out. They could understand how this building variations correlate to fabricability of the robots and the constraints that exist in building the structures just by using this very intuitive, tangible interface. And the students designed something, and then they also kind of watched the robot build what they actually designed all collectively. And with that, I want to close off by essentially sharing this framework of feedback loops that actually drives my work between matter, computation, and methods of making, and how this distributing intelligence in these subsystems across design, materials, and new methods of making can achieve perhaps a more ecological and inclusive practice. And to sum up, with what I presented today, I claim that no action is neutral. With every process and tool we author, we actually leave a trace on the systems that we design. And I shared kind of a selection of my work today, but I would like again to end with highlighting the cross-disciplinary aspects that made all of these projects possible, which is also the very reason why I decided to join this department, actually, as I believe that uncovering these synergies between design, engineering, sciences, and the humanities is essentially the only pathway for authoring systems that respect technological, economical needs, but also the social dimensions of labor, access, equity, and craft. So with that, I'd like to thank you for your attention and open the floor up for questions.
Thank you for such a wonderful lecture. Hopefully this is all being recorded so you can go back and rewatch everything, because several questions came to mind, but I'm going to try to pair two of them together. On the reconfig project, the large timbers coming together with two large robotic arms, I was wondering if you could elaborate on some of the safety protocols that were implemented for the human robotic interaction, as it relates to heavy timbers, also as it relates to dangerous soils. And then the second question kind of paired with that is, both robotic arms were on external tracks, and I'm wondering how you see this work potentially scaling up into the built environment, given that kind of constraint.
I'll start with the latter because it's technical and easy to get over. So of course it was like a lab setting experiment, but we could imagine either robots on mobile platforms. We could imagine also some stationary robots for selective tasks in construction site. For different tasks, you know, like if you're not carrying loads, then you could have also different types. There is a realistic limitation right now to this. But there is some kind of compromise between the payloads you are required to achieve and the type of robots you can use. And so there will always be some kind of compromise there. And for us, this was again a compromise on how do we think of this like 1-story or 2-story housing that can be actually have a realistic scenario of how we can tackle this. If we talk about multi-story buildings, that's a different situation. And then it becomes much more complex in doing that. But it doesn't mean that there will not be more development in the future on the robotic side. So maybe we see other things possible. and I think that there is some kind of key element there into cooperation also of robots. So you might need a certain type of robot to perform one task, but then it can transfer a subtask to a different type of robot. So we can be a little bit selective about this collective agency, I think. The safety protocols, that's a great question. There were different types of tasks involved. And so some tasks are more dangerous than the others. So there was some clear protocols where, for example, if a robot is in the process of using a chainsaw on site, then it's a clear understanding that everybody is outside of the construction site. That means that, you know, like everybody involved, all humans must be aware of what is happening at all times. It's not like you can just go do your thing and then the robots operate autonomously. I think, so I'm working with some researchers in the field of psychology and work psychology, that we're trying to understand, because some of it must be safety protocols, some of it is also matters of trust. How much do you trust an autonomous system that is operating next to you? And what are the elements that would break that barrier? So have actually workers feel comfortable in operating next to these machines. So some are softer protocols, some are kind of like very rigid because of serious safety reasons. There is other work that really tracks all the agents, and they have some kind of like boundary zones in which they can operate to actually make sure that there is no danger, but then again, limits a little bit the scope of this interaction. So from my perspective, I want to avoid that. I just want to find the essential protocols for safety and then actually allow with other methods to communicate a bit more intuitively and have kind of like the worker there feel in control and feel like they can trust what is happening at any given moment.
Thank you so much. That was an amazing lecture. I'm super inspired. This question doesn't have to do with the work per se, because I mean, I'm completely outside of the loop in terms of the sphere you're working in, but I'm just so amazed by the various disciplines that you bring together and the way that you're questioning from one project to the next, what you bring into play. And, you know, your last answer had to do with psychology. So I'm curious, you know, whether this could have been, this work could have been done outside of, let's say, the ETH, which is kind of a unique institution. I think it's different from something like MIT or Stanford, for instance, right? And so I'm curious, if we were to dream of, like, you know, a future academy that builds more of this kind of thinking, you know, covering everything from humanities and society to mathematics and advanced technology, what would it take? Or am I wrong? Are there other places already doing this? Thank you.
I think the unique setting of ETH is that it had a lot of resources. The other thing that can be more easily replicated in a way is the mindset of people. So this work was conducted within this framework of that was essentially a 12-year program to actually launch this new project in digital fabrication that actually essentially brought a lot of like-minded people together that wanted to cut across disciplines. And that's essentially a mindset that I think we're trying to cultivate into different places, hopefully also here in design tech. And the Future Academy, that's, I think, an ongoing conversation. I cannot claim to have the answer, but what I fear, or like what I want to advocate against, is kind of like producing this general list of the future. I don't think, in my perspective, that this is productive to have people that have a little bit of knowledge in many disciplines. It's good to have some knowledge in these different disciplines so you're able to communicate, but the true partnership comes where there's a grounded knowledge in a discipline, and then there's curiosity and ability to learn specific things that will allow you to form these exchanges. So if I were to dream from this Future Academy, it would be this kind of like very flexible program of being able to navigate between disciplines, but knowing where you stand, which is something that cannot be easily fit into a curriculum as we have it today, as we imagine today.
Hi, thanks so much. A lot of questions come into play. As you were explaining all of your projects, I began to think about scalability and, how does one move from the testing, the discovery, the questioning, and the prototyping to perhaps projects that are more applied, that have certain programs or resistance built into them. So, scalability, I guess, would shift depending upon the material and the connections that you're using. But would it be, it's always aggregations of unit-based? Would it be proliferation of connection, scale of connection? Would it obviously change on each one? I guess my question is, do you begin to think about these things as sort of constraints as you're designing this particular, for example, digital bamboo? Like, what happens when you want to make something much, much bigger? Do the joints get much, much larger? Do they proliferate? They stay the same, but you just have many more joints. So how does scalability factor into some of your research?
Yeah, great question. I think scalability is something that I think about all the time. And that has actually triggered a lot of the questions that resulted in projects. So for example, this question into metal manufacturing had to do a lot with scalability and cost and production. So in terms of systems, that's why I didn't just present the projects. I wanted to highlight that there is a framework behind it. And the idea for that is that, for me, this was a way to say that we need to think of a system of design and not just bring forward certain design typologies. And that is considering what kind of materials we're working with, what do we need to adapt in those small components. There is a computational framework that actually always detects the smallest volume that needs to be customized every part. So there is a component that I developed that says, this is really the smallest volume that we need to customize. So stripping down to the minimum. And then it's a matter of design, right? So for example, in the case of bamboo, we had this kind of a very small part that is custom, and then we have an interface that could be mass produced for that system. It can be different for a different system, but we can start to think about these ideas of customization and mass production, because we don't eventually need to customize everything we make. There is some value in mass-produced projects that we can leverage. Otherwise, the scalability of digital fabrication comes into question. Why do we need to customize everything? But the reality is that I am very much against implying that there should be a system that can be patchwork all around the world. We have different materials, we have different contexts, different levels and access to technology. So we must account for that, for the different systems that we design through this framework. That's why the idea was to have this kind of flexible design framework to do that. I don't know if that answers the question, but
Yeah, no,
just
it's,
an example.
I mean, putting it more just simply, like, this had to be 30 times as big because you needed to cover much more shade of a, would we have many more joints, or would the joints be totally different? Or would it would be a module-based system that then sort of repeats itself, and then there would be mega joints? But I mean, I guess I'm getting too
Right.
specific, but it's sort of not necessarily mass production and more, but just, what happens when it becomes bigger than a pavilion, or when it's bigger than the human being can, lift a piece of wood,
Right. No, these are fair questions, but again, that's a design decision more that is a technological decision. So we can decide to which extent we need our modules to be large. There were specific requirements for the modular project with the drones. They had to be of a certain size and of certain weight. If we imagine to build with different materials that can actually accommodate larger spans and bigger modules, we can do that. The joints will eventually be bigger if we employ larger sections, because the minimal volume required is bigger. So there is a trade-off between those components. How small do you want these components to be? Can we actually have a more refined structure? And that was very much part of the development of the digital bamboo. For that span, we could actually use 3 times the diameter of bamboo, but then we would have these massive connections and much refined space frame. So we used actually the smallest material we could get that is structural in order to minimize those elements and actually work with the rigidity of the system and the complexity and the hierarchy of the system to achieve that span.
Great. Yeah, no, thank you. Interesting question for me.
We have a question online from Kobe. Were there parts of your projects where you had to let go of control and let others drive the direction because of your different skill set? Where did this lead or change the designs in good to bad ways?
Sure. I mean, when you have collaborators in different disciplines, there is a shared drive and a shared goal, but there are different understandings of things and different priorities. So these you have to negotiate on the fly in a way. Depends who is leading the project. I feel like, as in any teamwork, there is someone that has a vision for something that might be rooted in a certain discipline, and that might help to guide or frame a bit this negotiation between things. But ultimately, you have to figure out a compromise because there's no perfect solution ever to anything. There is essentially investigation, options. You try to tackle from both directions, but essentially what you're doing is finding compromises between shared goals and disciplines. And we have to be flexible to do that. No pig-headed person has ever achieved through collaborative work like that. Yeah.
Hello. Thank you for the lecture. So in the digital bamboo project, you kind of mentioned that when you guys assembled the structure, you guys collaborated with the locals. And I'm wondering, so given that you are working with the people who might not have the specialized knowledge, then how did you come up with the structure in a way maybe the joinery is designed slightly different from the suggested algorithm, so that ease of assembly, the intuitive assembly, that's taken into account so that more people are able to assemble this more intuitively, that's benefited from the mass customization of the joinery part?
Great question. So in the other project that I saw, there was kind of like a very sequential assembly that needed to happen. In a digital bamboo, it's essentially you can start from any place. You can pick up two things and start putting them together like a puzzle. So they have connectivity tags that is imprinted within the elements that are printed. And then you can essentially start anywhere, pick up a part, see what it says, and then start building, and eventually you build the structure. So there's no special knowledge needed, no drawings needed. And basically we didn't need to give instructions to anybody to start assembling this. So it was super intuitive. We just showed them, you click this together, it actually makes a click sound, and then you put a zip tie and you move on to the next piece.
Was the algorithm kind of designed in this way intentionally, or it's just how the structure is, kind of has this feature inherently?
I mean, space frames are essentially networks, and so they allow for that kind of system. It's a question of tectonics, right? If you have a different constructive system, the connectivity of elements is much more rigid, and usually there's like a sequence of things that secure the transfer of loads and so on. And space frames are actually this kind of like points of connections and struts in between them. So inherently, there is an opportunity for that. And again, it's a matter of design. So this specific design, we thought about making it a modular structure. We decided not to do it. So it's really designed to just start building and eventually building the whole thing. When there are different requirements in the Protopolis project, because we wanted to achieve this kind of self-assembly and so on, there is a clear hierarchy embedded into that. So it's a different process of assembly and a different process and model of designing that structure.
Thank you.
Thank you. So you mentioned Japanese style architecture in part of the discussion, and how you were kind of pushed in that direction, or you moved in that kind of direction. I was curious, could or did traditional Japanese joinery that basically has a method for joining, individual stick-built parts, was it part of the discussion for this, or could it be part of the discussion as far as it seems like a lot of the challenge is how the parts get joined together. That was the challenge with the bamboo, and that's probably the challenge with the recycled beams. And I was just curious that it seems like there's thousands of years of history and craftsmanship in Japanese joints. And how would that kind of discussion affect what you have developed here?
I think the question is less about the style, and it's about more of designing for permanence or designing for disassembly and temporality. And the argument is that we need to more and more design for temporality. So designing for systems that will not be there forever, even if they exceed our lifetime. At some point, we should be able to reconfigure and take apart the system. So this typology offered an opportunity for that, and we did not consider redoing integral joints, because then we default back to designing for permanence. And so we could have this kind of like parallel system, and then have basically thread rods that kind of like connect the elements together, that would allow for very easy disassembly of the entire structure. There are other techniques, vernacular techniques, that do that, either with rope systems or even with this like kind of peg connections that can be removable. So there is a history to that, but I think it's more about, it was really not a decision to just copy a style. It was not a decision of style. It was rather a decision of how do we bulletproof this system for the future. We should not just reconfigure a structure with the same system just because we started like this. Obviously, there is so much challenge in deconstructing it right now. We should not default to the same problem that we started with. That was the motivation.
So the preference was for nodes and connectors that can be reused and reconfigured
Yeah.
elsewhere.
And also minimally processing the material, because once you imprint a specific joint typology into an element, then in the next life, then it's unlikely that you will be able to reuse this joint as it is. You will most probably either need to cut off this part and remanufacture it basically. So you always have this kind of like percentage of waste of material.
Okay, thank you. One more question. For the elements that we see on the screen there, did you consider investment casting? And if so, why would gel casting be maybe preferable to that for what you did here?
You mean for the metal?
Yeah,
piece?
for the metal parts, yeah.
Foundry casting is great, but it's kind of low resolution. There is like smaller, kind of like lower resolution because of the high temperature that the material is cast in. And for this type of joint, which is this big, you cannot achieve that level of detail without post-processing and machining the part. So what you could do is basically cast a rough shape and then try to machine it. This is so complex and it has like so many integrated details into it that the only way to produce this typology of joint is to basically 3D print it. And so it's almost out of the question. Like even if you 3D print the mold for foundry casting, you cannot achieve this level of resolution.
Okay, I might disagree with you on that, but I'll catch up with you later. How about that?
We can talk. I have a lot of experience with metal
Yeah,
casting.
yeah, let's talk. I'd be interested to hear more about that.
Yeah.
Thank you.
Thank you, Marirena, for a really excellent and inspiring lecture. I'm curious, in your mission to shift the gender imbalance in the construction industry, how are you thinking about engagement and collaboration, especially in the really exciting possibility to kind of accelerate access through emerging tech and robotics and bridging this divide between years of talent in traditional building crafts with robotic construction?
Yeah.
Just curious to hear more about your thoughts around engagement and collaboration with other audiences.
Yeah. I think changing the mindsets is never easy. But also that there are pathways of doing that with outreach, with small communities that have a mission to change things and partnering with them to kind of understand how we can have better outreach. But I think there's also a component of research there because we need to understand. One thing is to understand what has happened so far, which in this case, it's okay. It's a physically taxing job. It has been primarily a type of work that is actually considered manly or that requires physical strength. There's also components to that. But then when you try to think of new solutions and new opportunities, you can actually reach people that might be excited for a new type of work. And that is not gender specific. So figuring out what are the components, and this is what we're really trying to understand with these collaborators, are there elements or qualities in the interaction modalities that we can that can have impact into accessing these different target groups. For example, through some surveys, they found out that actually if you create kind of like a lifelike response, this is especially appealing to women for some reason. This makes them feel more comfortable with the system in comparison to men. Men perhaps don't need that. So it's also a question about how do we design technology and who do we design technology for? Because a lot of times we're just going to that place where they do something, try to understand how they do it, and then figure out a way to automate it. But if you want to change the discourse, you need to also understand why is that workplace like this composed, and what are the elements that we're missing that we can bring with technology in order to change that. And then have the outreach and the user studies and try to validate that assumption.
Thank you. We have one final question online here from Gia. Thank you for the wonderful lecture. My question is, since each of your design processes is so uniquely tailored to the specific project, I'm curious, how do you see these methods being adapted or incorporated into commercial projects, especially when time becomes such a critical factor? Do you think the dynamic between human and machine collaboration could scale to fit fast-paced demands of commercial production? And then she states, not referring to mass production, but just general non-research-based design timelines in design and construction.
Well, there is an element. So, for example, with the space frame structures, there is an element to this design framework that would allow for, also projects that are not so research-based. So if you're working with known materials and properties, you can essentially have a very fast output to that. As you would do with any architectural project, right? There is still an element of design. I think with these robotic tasks, what's probably will end up happening is that the way you can generalize this is not looking at a specific process, but actually crafting specific tasks and interactions. And then depending on the process you want to achieve, you can actually mix and match those tasks and interactions. That's kind of a way that we can be more adaptive about how we develop the systems, because it's not really sustainable in just developing an automation process for a specific type of task and a specific type of structure. At least in construction. In other industries it makes sense, and those are industries that have been automated, but not in our discipline. So it's a task-based job, and this is what we should think about, how we automate this, and not how do we automate a specific system or typology. Because it's not viable to essentially build a robotic setup every time you want to do a single project. That's kind of it's a highly complex problem to do that. Yeah.
All right. Thank you so much, Marirena, and thank you everyone for joining us this evening in person and online. Please join me in a round of applause for a really great lecture.